Okay, this is about, honestly, I can't quite remember where we left off, but let's assume it's around here. If this is review, it's review, which is never a bad thing, right? So we're defining the link stack. Remember, the idea is we have size as a field, and we have a reference to the top. If it's an empty stack, top will be null. If it's not, we'll have a chain, a link structure of the elements in the stack, where the top of the stack is the thing at the front of this link structure. I'm pretty sure we covered this pretty well, but let's just keep going anyways. So here's the general idea. It's generic. We have a node that's also generic. Top. Yeah, we definitely did cover this. I'm going to go quickly because I remember talking about the internal node class. Yeah, it's all your fault. The internal node class. So we have top, size. Start with an empty stack. Top is null. Size is 0. And then push. Well, push will take the element we want to add, or push, create a new node with the element in it. The new node's top, or next will be the top, and then top will be the new node. That's just inserting at the front of a link structure. Pop, if it's empty, throw an exception. Otherwise, get the data, move the top to the next, which is just removing from the front of a link structure, return the data, decrease size. Peek is simpler because we don't actually have to remove anything. Is empty with size is 0, and size is just return size. And then last time we talked about the idea how, there are a couple of other ways we could do is empty. Like we could say like if top is null, we know it's empty. Yeah, that would also work. We've got a lot of options. Whenever you're in a situation where you have multiple reasonably good solutions to a problem, you end up spending a lot of time thinking like, well, which one's the best one to use, right? And it might feel like that's a big waste of time, but I don't know. I like this one because it adds a little bit more intentionality. It's a little clearer. Someone who might not know much about the inner workings of this class, if they see top is null means it's empty, they might go like, why? Where here if they see, well, size 0, it's empty, they're probably less it's probably a little clearer, I think at least. But does it really matter? No. ToString, same idea as the other one, create a stack, but because, remember with the array stack, the top was always at the other end, but I wanted it to be printed such that the top was at this end. We did that funny thing with that string builder where we kept adding to the front, such that the last thing would be at the front. Here we don't need to do that because the top is also at the front. So start at the front of the stack, which is also the top of the stack, and then keep going. And then our equals, we've got our checks. Is it the same thing? Is it null? Is it even the same class? If they are, first check if their sizes are the same. If their sizes aren't the same, they're not equal. No sense checking further. But if their sizes are the same, create a little iterator references. We'll call these the iterator ones, the ones that start at the front and they move down the two stacks, link structures in like coordinated like this and that, this for this, that for that, and check that they're all equal. You'll notice here, well, current's not null and that current is not null. Kind of unnecessary. If I know they're the same size, it's not possible to have one exist and one not exist. Because if stacks have size x, they must both have x nodes. So it's impossible for them to not always exist or not exist at the same time. But again, it's that intentionality, like the meaning of the code. Yeah. His hand first, yeah.
We talked about it in the other stack, but why in the equals, in the diamond method, the diamond operator, it's a question mark instead of
So it's complicated. But the reality is at this time, whenever it's I'm not going to get into the full details because it really is beyond the scope of this course. And my understanding of it is always like, I always have to like re-remember every time. But here's what I remember. Here's how I make it make sense to me. When it's T, everything in here must be T, okay? Upon creation, if it's a string, it's a string. But when I'm doing equals, the other node, like the other stack, might not be of type T. So like, I don't actually know what the types are. But they'll be objects, and because they're objects, I can check equality on the objects. But as far as I know, like, they might not actually be T. That's kind of what it is. Yeah?
About the null thing, aren't we already checking if it's null before?
Well, only the top. Only if, well, first we're checking if the other object is null, right? But I exist. And then here, now we're checking if the top is null. So presumably if I exist and sizes are, just think about it. It's all about like what's null. So if I exist, meaning you're asking me, hey, do I equal something, right? So like if I am my stack, I'm a reference variable to me, my stack. You can't ask me if I equal something if I don't exist. So I must exist, okay? But does the other one exist, right? You're asking me, hey, do I equal that thing? Well, does that thing exist? That's what this first check here is, okay? Then when it comes down to here, I'm saying, okay, so I have this, which is a reference to some stack. I'm representing as a circle. Obviously, this is, I exist, I'm me, right? I know that that exists. Okay? And each of these has a in top. I'm writing really small. Hopefully you this is just top. Okay? That is a reference to some node. Okay? If they assume they have the same size, their sizes could be 0, so these references could actually both be to null. Doesn't really matter. But presumably, in a more general case, we've got something like this. Can you see this at the back reasonably well? I know I'm writing small. I don't know why I'm writing so small. So what I want to do is this current is pointing to the top. That current is pointing to the top. I check, are their contents equal? If they are, go to the next two. That's what this is going there. This is always checking, are they not equal? Because they're equal. They're equal. They're not equal. Oh, well, now I know they're not equal. It's a linear search, but it's kind of like the flip of what we've been doing in the past, where like when you're looking for something. But here, what am I looking for? When you're doing a linear search, the moment you find what you're looking for, you found it. Here, what am I looking for? I'm looking for if they're not equal. So the moment I know anything's not equal, I know they're not equal. Cool? Cool. Good question, though. This is a good review. And then we talked about this nested node class. And the whole motivation of this was, look, this is entirely not a requirement, but it's a nice thing to do with your code because, you know, this node class, we could just make it a regular class and, you know, use it in another class like everything else we've done so far. But, you know, this node class is like a whole class that's important for the inner workings of this link structure. So really, like this node class has no utility outside of the class in which it's used in. So in a similar way where I can have like a private method where like, well, this method is useful inside a class, but it's not really useful elsewhere. So let's just put it inside the class. The same idea exists for whole objects, for whole classes. We could define a class that's useful for the inner workings of this class, but not really anywhere else. So we make it a private static inner class. And it's exactly the same as what we discovered, but this is just within the node class. So this is a nested class, which we already saw in the unit tests, but done for a different reason. I mean, kind of the same reason in the sense that it's for just nice bookkeeping, but yeah. Any questions about this linked stack? And if we look at this code, just one sec, here, this code would be the exact same like playing around code as the array stack. All you have to change, like I was saying, because this is a stack, and all this cares about is that this reference variable references something that's a stack. And a linked stack is a stack. I could change this to an array stack, and all this code will work just fine. Under the hood, it works a little differently, but at this level of abstraction, it's a stack. Push, pop, peek, whatever. You had a question.
About the nested class, does it have to be private?
I can't quite remember. There are a bunch of rules, and that's like a Java thing. There are a bunch of rules And I can't quite remember if it's like static or non-static. I think, I can't quite remember. I really can't quite remember. But it doesn't overly matter too much. But, you know, when doing it, do it that way because we know it works. But that'd be like a Java-ism. Yeah. All right. Yes. And then we start talking about algorithm analysis. Is this looking familiar to you? Yeah. Okay, good. All right, so algorithm analysis. But what does it mean for one algorithm to be better than another algorithm? Well, is it lines of code? No. Is it the number of like floating point operations? Maybe. Is it the amount of like time your algorithm takes? Kind of. But really what it comes down to a lot of times is like time complexity and space complexity, and sometimes people talk about like processor complexity. But basically, if you have one algorithm that fundamentally will take less steps than another algorithm, and when I say less, I don't mean like mine took one fewer steps than yours. That's really not what we're getting at. I mean something like if your algorithm, if I have a problem where the input size is n, and your algorithm takes n steps, but theirs takes n squared steps, n squared sucks. N is good, right? Like linear is better, right? We want like fewer steps. And also things that take up less space is good too. But you'll notice as we carry on, there's no free lunch. Anyone ever hear that phrase before, no free lunch? There's no silver bullet. There's no free lunch. You win some, you lose some. It gets better here, it gets worse here. It gets better there, but it gets worse here. There's always a trade-off that you're playing. All right. So the big thing that we're going to focus on is time complexity. That's the things like a linear search. If you have n things in that list, how many things do you have to look at to guarantee if you find it or not? N. Like that's that idea, right? So how long does it take to sort 10 items versus 10,000 items, for example? When we talk about time complexity, we really are always thinking about it relative to some input size, where the input size really depends on the problem that we're talking about, like what is like the number of elements to be sorted, the size of the list to be searched. That's like the input size. So to do this, what we do is we consider the number of like our basic operations needed for the algorithm to do its thing. And these are going to be things like our additions, our comparisons, all of these like nice basic units of computation. That when you boil all this stuff down, it comes down to a lot of moving data around additions and comparisons. That's a lot of what our code is. So with an understanding of an algorithm's time complexity, if I have a suite of algorithms and I have a particular problem that I want to solve, and a suite of algorithms for those problems, knowing about time complexity can help me make an informed decision on what algorithm I should use for a certain problem. And it's interesting because of this no free lunch thing, it's like, it's not even like this algorithm is better than this algorithm, but sometimes it's like this algorithm is better than this algorithm under certain specific conditions. And this one's better than this one in other different conditions. So if you know something about your problem, and you know about your algorithms, you can make good decisions about speeding things up. And I know this sounds like really abstract, but like I have buddies that are software engineers that when they spend time thinking about this, they save their companies hundreds of thousands of dollars. Like my buddy, he got a new job at a company, and within his first week, he submitted a pull request to change their thing, and he saved them like $50,000 a year. Just by like, oh, look at that, we can fix this. Like, this has huge implications. So like this is important stuff. Now you got to think these companies have like massive amounts of data being stored in like cloud, right? So like that's where like you get those speed ups and save money. But very important stuff. Okay. So how do we actually start thinking about analyzing these algorithms? We often like to talk about these algorithms at a fairly high level, like this analysis at a high level. And I'll show you what I mean by that clearly very shortly. In this course, I'm going to show you how to do it at a level that's sufficient for this course. But what I'm about to show you really isn't that rigorous, all right? If you take like 255 next year, you're going to do this in a lot more detail. If you discrete math next year, you're going to do this in more detail. And it's a lot of fun, don't get me wrong. But right now, we're going to keep it fairly high level, which will be good enough for what we need to do, because it gives us the intuition. We start with something called a growth function. All right? T of n. It's a function. All right? It could be something like T of n equals 2 times n, right? Like, how many steps does my algorithm take, right? Well, if my list is length n, this is how many steps it's going to take, for example. Like, that's what I mean, okay? That's the T of n. Now, how I find this T of n is relatively straightforward, but we're going to cover that in a moment. But let's say we have a magic T of n function. You gave me an algorithm, I looked at it, and I told you, based on what this algorithm looks like, this is the T of n. T of n is 15n squared plus 45n. Okay? Where did it come from? It doesn't matter right now, but that's the calculation, right? So this is the growth function. Here's some algorithm. It's a very important algorithm, and this is how many steps it takes to run, based on some input size n. Now, what does that mean in like raw numbers? Well, let's say, okay, if my input size was 1, how much time is it going to take? Okay, well, 15n squared is, well, that's 15, 45n, 45, the total is 60. And then over here, I'm showing you the proportion of, now we already kind of talked about this, I think. But like, here, we'll come back to this column. The next line, if n is 2, all right, well, the 15, if you plug 2 into that part, it's 60, 90. All right, so, you know, this one's clearly worse. The total's 150. But, you know, as n grows, the n squared part grows a lot worse than the regular old linear part, right? Now, if this is blowing your mind, just remember like grade 5. Okay, maybe it was grade 6, I don't know. Like, this will grow faster than this. Squared numbers get bigger relative to not squared numbers. So as we go, like if n is 1,000,000, the 45 or 15n squared is going to be, what is that? Million, billion, 15 trillion. That's a lot of steps. And the 45n is 45 million. Look, I'm not saying 45 million isn't a big number, but it ain't no 15 trillion. When you look at the sum of the two, like, what is it? That's pathetic. And look, if you look over here, I'm showing you the proportion of the whole, the ratio between the 15n squared part and the total. Basically, how much of the total can the 15n squared account for? Well, as n gets bigger and bigger and bigger, it starts to account for more and more and more and more. In our case here, at 1,000,000, it accounts for 99.9997%. Most of it. And as n grows, it's going to take up more and more and more. So you can actually start to quickly get a sense that, like, when n gets big, which, by the way, when we do this analysis of these algorithms, we're always thinking n is some catastrophically huge number, right? 1,000,000 is small compared to what we care about, all right? So when you look at this, it should be quite clear that, like, okay, one of these two things dominates, right? If you're playing the blame game, who's to blame? This guy right here is definitely to blame. This guy, it's nothing. It's inconsequential. And as n grows, it gets more and more inconsequential. So, yeah, who gets blamed? The n squared part. And if we plot these, like, look, I'm plotting, this is all because of scale. Mind the y-axis. As n grows, and this only goes up to 10,000 here, by the way, not to 1,000,000. As n, I'm plotting the squared versus the linear versus the total. Which, by the way, you might look at this and be like, well, where's the blue line? It's perfectly covered by the green line because this yellowy orange line is completely useless. It's, when you look at it at this scale, it's flat. It's almost like it's a 0. We know it's not a 0 because it's 45 times n. But 45 times n at this scale is so meaningless that there's nothing here, right? Like, and this is times 10 to the 13 up here, okay? So, yeah, it's nothing. It's so inconsequential that you can't even see the difference. Like, this is so inconsequential that the sum of this plus this looks exactly like this. Does that make sense? Right? Yeah, cool. So in other words, we don't care about anything other than the dominating term. And yes, we are that lazy in computer science. We go straight to what we call like big O notation. Okay, I will give you a warning. Okay, this is an important thing I want to emphasize here. One thing students, when they learn this the first time, they tend to miss. I try to emphasize it, but I don't blame them for kind of missing the point. So I'm going to try to really emphasize the point here. Students tend to miss when first learning about the computational complexity is that the function describes how things change relative to n. At this stage, the discussion is not about any absolute runtime value. It's more about, if I double n, how much more work is there? Not an absolute value. It's always about like the changing. So given a growth function n squared plus 999n, one may say that the 999n part of the function is going to dominate for the first 999 values, which is true, but this is not the point of computational complexity analysis. The point is identifying which part of the function grows faster, and in this example, n squared grows faster. This is not to suggest that the observing that when n is less than 999 is not important. That's not, no, of course it's important. If your problem is always n is less than 500, well then this is valuable information. But it's about thinking things at scale, large, how does it grow, okay? All right, so asymptotic growth and big O notation. So first and foremost, as we saw, it was 15n squared plus 45n, but 45n was entirely useless. So what we do as computer scientists is we immediately look for what's the blame game, who's to blame? Who's accounting for most of the problem? And because we don't like overly nuanced functions or expressions, what we do is we also like to talk about what we say is asymptotic complexity. We want to say our growth function grows like this nice clean function, okay? And we have a nice set of growth functions that we usually play around with. There's more, don't get me wrong, you can get as precise as you want, but often we keep it to these nice simple growth functions, or these functions that we say big O, you'll see. All right, so the order of the algorithm is specified using big O notation. So the order of the algorithm is, yeah, okay. So the above example T of n, 15n squared plus 45n, has an order of like a big O of n squared, since it grows like n squared. Okay? So I went from 15n squared plus 45n. Was there any constant? Did I? Okay, then no constant, right? And I'm saying, nah, this is basically like n squared. So I've immediately, and I showed you, that this part is meaningless. It's effectively, it's nonsense, it's noise, okay? So we don't really care about that. We care about this part. But I went from 15n squared down to n squared, okay? And you're like, well, what about the 15? Remember, what does it grow like is what I care about. The amount of work will change. The 15 is still there. If I made n twice as big, the total amount of work is going to be n squared more. Like if I doubled, let's say n is equal to n, all right? Okay, so that's the total amount of work that this will happen. But I'm talking about how does it scale. So if I say, well, let's say n is now 2n, okay? So the total amount of work will be 15 times 2n squared, okay? But how much it actually changed is just the n squared. It's 2n squared. So like, right? Right? So that's what I care about. This right here, I don't actually care about these coefficients because it doesn't mean anything about like as I'm scaling n. Yeah, the growth, it still exists in the total number of steps, but we're not talking about the absolute total number of steps. We're talking about how does it change as we scale n up. As we crank n up, how does the total amount of work change? It changes like this. And we always look for these nice, clean growth functions. Or, yeah, okay, here, let's do a quick test. Oh no, this one's not a test, it's just examples. If I had something that's t of n, 17, no matter what the size of n is, my algorithm takes 17 steps. So what I would say in this case is that's O1. And you're going to say, well, no, it takes 17 steps. Yes, but this is how my work changes relative to n. If n is 1, it's 17 steps. If it's a billion, it's 17 steps. It's constant. 1, it means nothing. 20n minus 4, that would be big O of n. Okay? That's how it changes as we crank up n. 12n log base 2 of n. By the way, whenever you see log in this class, it's going to be base 2. If you don't see a base 2, assume it's base 2 unless specified otherwise. Raise your hand if you remember what log means. Okay. So I'll assume half of you are kind of like, I remember hearing about I don't want to look stupid. Don't worry. Log is just the opposite of like to the power of. Okay? You know how like division is like the opposite of multiplication? Subtraction is like the opposite of addition? Well, the log of a base is like the same as like to the power of. 2 to the power of n is the same as like, you undo that by doing log base 2 of n, by the way. Anyways. So 12n log base 2 of n plus 100n. This would be n log base 2 of n. 3n squared plus 5n minus 2, n squared. 2 to the n plus 3n, that's bad, by the way. If your algorithm is 2 to the power of, ooh. But you know what? There are problems out there where the algorithms, that's kind of what we're stuck with. But it sucks, okay? Like this is where, yeah. Someone type in 2 to the power of a million.
It won't display that.
It won't. What's up?
Could be worse, could be n to the power of n.
Of course it could. We could have a lot of fun. 2 to the power of, let's do 2 to the power of 100 for fun. Yeah, we're in trouble. So you had an algorithm where the input size was 100, which isn't even that big. And you're looking at that. What about 1,000? Whew! That's more than like, that's like, I always say like, how many atoms in the universe? What?
Thank you, Google AI.
Man, I can't, AI is changing the world, Holy moly. I really wish it was like, I would at least be amused if it was like, what? This is ridiculous.
Explanation, since we can't count every atom in the universe.
We can't count that many, it's probably about that many. All right, like what is this even? All right, fine. Is there like a feedback?
At least it's a whole number. Yeah, just thumbs down
Boom. All right, there you go.
in the world.
I was hoping it was going to be like, there's at least 1,000. All right, well, let's, there we go. So in the universe is a vast range, considerable unknown. Let's estimate there's between 10 to the 78 to 10 to 82 atoms in the known universe.
So it's just not squared.
This square.
Oh,
That makes more sense.
it didn't.
That's more.
There you go. It had an issue with typesetting. At least, okay, look.
Okay, that's
Now I feel kind of bad.
no, that's still a thumbs down. But,
You think so?
oh yeah.
Okay, all right, yeah. Yeah, because that could have caused a problem, right?
That's a lot better.
That's a very big difference.
It's still bad, but we've got an explanation. Yeah,
at least
okay.
You can feel bad for it.
Yeah. You're like, oh, like we now know why it's stupid.
Yeah.
Yeah, we have an explanation. It doesn't make it okay, but we can explain it. I understand.
It feels more like a try.
Yeah, yeah, good job. All right, anyways, times 10 to the 82 on the upper bounds, yeah, I mean, if you had like, and like 1,000 is like n of 1,000, and that's a small number. Like when we're talking like n, we're thinking like the big boys, right? That's itty bitty. That's not, but 1,000 is. So 2 to the, oof, yeah, we're in trouble. Big numbers, man, they're crazy. Anyways, so these, like this kind of like shows you like, okay, the scale. Okay, if something's linear, n log n is worse than linear, but it's better than n squared, right? If you're like, how am I going to remember that? Well, log of n is smaller than n, right? If you had n and a log of n, if you log something, it gets like smaller, okay? So log of n, if there was a log of n here, it would be below here, okay? And n times n is going to be bigger than n times something that's smaller than n, log n, right? So it's like in between. You could end up with these ones where it's like n log of n, but we don't really talk about those ones. We keep it simple. So here's a quiz. All right, everybody, on the count of 3. We have a growth function of 5n squared plus 3 of n. Big O is 1, 2, 3.
N squared.
Nice. All right, n cubed plus log base 2 of n minus 4. 1, 2, 3. N cubed, right? 10n log base 2 of n plus 5. N log n. Very good. That was a tricky one. 3n cubed plus 3n squared plus 3. Go. N cubed, and then, oh, this one's tricky. 2 to the n plus 18 n to the 10. It's going to be 2 to the n. I know you're left going like, well, you know, no. Don't overthink it. That sucks really bad, okay? If you go to Wikipedia, you can find like the common ones. There's like, look, okay, so order 1. And they're in order from like good to bad. If you have an algorithm that solves your problem and it's constant time, you are a very happy person. Everyone's happy with you. Then we have this like alpha n, I don't know, who cares? You never see that. Log n, you never really see that. Log of n. That's usually what we're going to see. You go from constant, and then the next one we usually come across is, well, something that takes log of n. Okay? Remember last semester how we did a linear search? That was linear. But we also did something else. We did that like that phone book thing, right? Or a textbook. If I'm looking for a page in the textbook, I'm able to like make a decision, right? Remember I did that, like pick a number between 1 and 1,000, right? And I was able to guess it in like 10 steps. 10 is a lot less than 1,000. How was I able to do that? It's because I was using an algorithm that was log of n. That's why. And why was it log of n? Well, because every guess I made, I eliminated half of the questions, right? I said pick a number between like 1 and 10, 24, right? And I started with 5, 12. You said higher or lower. If you said higher, no, if you said lower, okay, I could take all of the numbers, 5, 13, and 5, 12 technically, 5, 12 to 1,024, throw them away. I don't need to look at them anymore. But, so like with one guess, I was able to eliminate half of the things. My next guess would be 256, right? You say higher or lower. If you say lower, I'm able to throw away 256 to 512, 511. Throw them away. I eliminated half of what was remaining. I'm dividing by every guess I make, I'm able to eliminate half of the things. I divide the remaining number of numbers by 2, repeatedly. And if you keep dividing by 2 several times, that's log base 2. That's what that is, right? You're halving, and then you're halving, and then you're halving. It's the opposite of doubling and doubling and doubling, right? Which is 2 to the power of, but log base 2 is the opposite of that. Cool? Cool. That's an example of a logarithmic algorithm. And then we have this log to some constant. You don't really see that very often, for ours at least. And then n to the power of some constant where it's less than 1, linear, n log n, n squared, n to some constant, c to the n, and then n factorial. That's a bad one. Oh yeah, real bad, right? So the ones we often will see, like in this course, you're going to see like constant, log n, linear, n log n, n squared, n cubed, and c to the n, that would be like some constant to some power. That'd be like 2 to the n, for example. And then factorial, we won't really see it, but I can give you an example of one of those. Remember I talked last semester about traveling salesman problem, right? That would be an example of like a factorial one, right? Why? Look, if I have to visit all those cities, and I have 1, 2, 3, 4, 5. If I'm, just to review the problem, I'm a salesman. There. And I need to visit all these cities, right? But I want to save on gas. So I don't want to go from like here to here to here to here to here. No, I want to have like a nice path that like minimizes the total distance traveled. Very simple little easy example, right? So, I want to visit all these cities. I want to start here because I live here. It's my house. I live there, so I want to start here and end here for the day, right? So I want to connect these dots such that I minimize the total distance traveled. Make sense? So, okay, how did you find a solution to this problem? Easy. Try all the paths and find the shortest path, right? Make sense? You don't have to overthink it. Yeah, but we got a problem. And you're saying why? Like, that algorithm is simple, makes perfect sense. Yes. However, how many paths are there? Let's think about it. Now, in our example, we have 5 cities, and the starting city is fixed. Okay? So really, here, how many choices do I have? 4. And then let's say I went to here. After making one choice, how many remaining choices do I have?
3.
Right? That's factorial, right? If you're like, why multiply? Come on, don't you remember like grade 5? Like, if you have 2 pairs of shirts and 3 pairs of shorts, how many combinations do you have? You just multiply them, right? So how many choices do you have in total? You multiply them out of all the possibilities you have. So whenever you have n, it's really like n minus 1 factorial, and you can divide by 2 because forward and backwards are the same. Long story short, you'd look at this and be like, that grows like factorial, right? And so TSP, problem. Yeah?
Would that be like O n minus 1 factorial?
No, this would be like, oh, the growth function looks like this. But we would be like, that's big O of n factorial. Yeah. You could nerd out and be like, well, really we want to lower the bounds. And no, it sucks, okay? Because it's always like, what does it grow like? It grows like this, okay? It doesn't grow like this. It doesn't grow like this, and so on. And yeah, you thought this was bad. What is 1,000 factorial? It doesn't even, right? I like how it's like here. The number.
Wait, you scroll down to the people also ask it. It says what is 1,000 factorial?
Well, let's be nicer. Let's do like. No. 100. Yeah, we're at a big number. Yikes, we're in trouble, right? We'll do 200. Yeah, it's not even. it's just like, no, I'm not going to calculate it. Stop it. All right, so we did the quiz. Cool. So I told you how to go from a growth function to big O. But I never told you how to get the growth function, so let's talk about how we can find the growth function. First, I'm going to show you the rigorous way, and then I'm going to show you but here's the trick. So some growth function is derived by investigating the code. So, okay, for simplicity, constant time statements will be said to take 1 unit of work, when in reality, it might actually take several units of work, but because it's constant time, it really doesn't matter. What I mean is like, adding 2 numbers together, I will say takes the same amount of work as like saving a variable, for example. Even though there might actually be a discrepancy, but because it's constant time either way, it doesn't matter for us at all. So I'm going to just say, I'm going to count every like just statement as like, okay, 1 unit of work. All right, so for example, each just like simple little statement like this is 1 unit of work. Assign a value, okay, 1 unit of work. Assign a value, 1 unit of work. X, Y, okay, 1 unit of work. Now when I say 1 unit of work, like I was just saying, there are more steps involved. Like think about what your computer needs to do. Your computer needs to go, okay, I'm going to set aside a variable somewhere in RAM. I need to load this value into that location in RAM and remember where it is. Like there's a couple of steps that the computer needs to actually do. But for our needs, just it's like 1, 1, 1. If this was your algorithm, I would say, well, the total, like the growth function for the entirety of this code is T of n is 3. Which of course is, well, that's just constant time, big O of 1. Okay? Okay. Now, loops. Okay. There's no trick to it other than knowing what a loop is. So, how much work is happening here? Well, I have 1 unit of work here, and this right here, line 3, is 1 unit of work. However, the number of times that 1 unit of work runs is variable based on n. Now, here I use the variable n. I could call it whatever. But the total amount of work here is 1 unit of work n times. So 1 times n. Meaning that in this example, we have 1 unit of work plus 1 times n, one thing n times. Okay? So you look at this and you go, well, big O of n, obviously. Right? Cool. If you wanted, okay, with a loop, consider a number line. Right here I've represented a number line. The ith number in the number line is visited each time. I always like to think of it like, okay, how many things do I have to put my finger on? Okay, for the loop, 1, 2, 3, 4. You know, like that's, the loop's running that many times, right? Yeah? Now, if you have nested loops, it can feel like this is where things get tricky, but only if you try to skip steps in your head. Just keep it simple. What are the rules, right? Okay, how much work is being done? 1 unit of work, 1 unit of work. Okay, now, the nested loops. Okay, how many times is this being run? Okay, look. Let's jump down to line 6. Line 6 is 1 unit of work. But this line is being run n times, right? But this loop is being run n times, right? So we have 1 times n times n. N squared. See, it's really not too bad. But it's complicated because it's, okay, 1 times n plus 1 times n plus 2. Right, that's exactly what I said. Well, okay, 1 times n plus 1 times n plus 2. And, you know, we can multiply it out. We get n squared plus n plus 2. Right? And you look at this. Okay, well, it's big O n squared. Right? And then, yeah. So instead of thinking like a number line, think a square, right? We're running n things n times. So we now have like a table. How many things do I have to put my finger on? All of these. And then do it again. And then do it again. Nested loops. In this case, it's like n squared. Cool. Any questions? I'm going quick, but it looks like you're pretty happy. Yeah? All right. So, what's this one? Here's a quiz. Not an activity. I didn't give you enough time to write. I should have done it. But take a moment, look at this, talk amongst yourselves. What's big O of this? Like what's the growth function? What's big O of this?
Are the states in the for loop, like the end I equals 0, does that count as 1?
Hey, it would, but it's constant, so we just really don't care. But interesting question, but we really wouldn't care. But you're right, like we would need to create the variable, assign it 0, and increment it every time. You're right, yeah. So how many times is this running? Well, here, look, the trick of this is like, okay, it's not I plus plus, it's I equals I plus 2. So if you go back to, do I have it here? The number line, it would go 0, 2, 4, and so on, right? Yeah? Are you sure? You're happy? What's 0 plus 2?
2.
What's 2 plus 2?
4.
What's 4 plus 2? Okay, so you do know. Okay, good. But, so how many times is this loop going to run? From 0 to n, how many times will this loop run? Will it run n times?
No.
How many times will it run? N over 2. So T of n is going to be like, okay, 1 over 2n plus 1, right? If you don't like, fine, we could do, okay, whatever, right? But this is just like a coefficient, and we don't care. The amount of work this would do grows like n. So it's still n, even though it's half of n, yes, but it grows like n as n grows. Like the amount of work being done grows like n as you crank up n. That's what I'm saying. You have a question?
It was about one of the ones earlier.
Was I making a mistake? Earlier today, I kept saying 19 plus 4 was 22.
It was the nested loop.
Pardon?
The nested loop one. Where did the plus 2 come from?
These two.
Those two.
That's all. It's just like plus 2 additional units, but it's so inconsequential, it just doesn't matter. But good question. All right, so this one. Ooh. Here's a tricky one. The trick here is j doesn't start at 0. J starts at I. So the first time through the loop, I is 0, j starts at 0. The next time through the loop, j starts at 1. Then the next time it starts at 2, and so on. All right, we'll pick up here next time because we're out of time. This is a good one, and the next one's even more fun. And look at this. What's going on here? Wow. Anyways. For the longest time, I had a typo in here, and this was 0, and students were always like, it never changes. Like, okay, fine. All right.